All right, so a little bit more with limits. In the last video, we talked about some discontinuities, and we focused on these three different types of discontinuities. And in this video, I really want to focus on this jump type of discontinuity and how it differs from this removable discontinuity or this hole. Over here, if we're considering the limit as x approaches 5, the way to think about it is, even though the function is not defined at 5, the function is defined if I'm a little bit less than 5 or a little bit more than 5. So I consider the output to the function when the input is slightly less than 5 and slightly more than 5, and I see that in either case, the output is really close to 8, and therefore I conclude that the limit as x approaches 5 of this function is 8. But that same logic won't work over here with a jump discontinuity. Right? Over here, if we call this function, I don't know, f of x maybe, we can evaluate f of 1. It's no problem. Because this circle right here is closed, when we put 1 into the machine, 1 comes out. However, if you think about the limit as x approaches 1 of this function f of x, it's a lot more difficult. And the reason why is because if our x value is slightly less than 1, then our output is slightly less than 1. But if our x value is slightly more than 1, well, then our output's nowhere near 1, right? It gets kind of close to 3. So really, when we talk about the limit as x approaches 1, it's a more complicated concept. Is it really close to 1, or is it really close to 3? Well, it kind of depends. It depends on whether we're looking at the limit from the left side of x equals 1 or the right side of x equals 1. And that concept is what we're going to get into in this video as we talk about one-sided limits. A quick caveat here. For the purposes of our class, one-sided limits are only going to be an issue when we're looking at limits geometrically, when we're given the graph of a function. So here's a perfectly good graph of a function. Again, maybe I'll call it f of x. And let's look at what's going on. One of the discontinuities happens at 4, right? Here's where x equals 4. What I want is a way to express that when the x value is slightly less than 4, the y value is slightly less than -7, it looks like down here. And when the x value is slightly more than 4, the y value is slightly more than, I don't know, -1 or whatever this point is supposed to be. How do I capture those ideas? With what are called one-sided limits. So this notation right here, the way you read this is the limit as x approaches 4 from the left side of this function f of x. The from the left side is the part that's new in this video, and that's captured by this little minus sign here, typically written up in the superscript of the 4. So even though I couldn't format things perfectly here, maybe it should have looked like the limit as x approaches 4 from the negative side of this function f of x. And all you have to know about this is think f of, I don't know, 3.999 and not f of 4.001. Why? Because we're coming from the left. How do I know we're coming from the left? Because of this little minus sign, right? Negative numbers are on the left on your number line, positive numbers are on the right. When I put this superscript of a negative here, it just means from the left. That's it. If somebody asks you the limit as x approaches 4 from the left of f of x, this question that you see written right here, the way you would answer this is you'd look at this graph and you'd think about what height am I getting really close to when I approach 4 from the right here. That height looks like a -7, so the answer is -7. Contrast that with this limit right below, where we're asked to figure out the limit as x approaches 4 from the positive side of f of x, or from the right side. We still come to our graph and look for the x value of 4, but now we don't walk towards, if you want, that value from the left. We walk towards it from the right. We start on the positive side and walk towards 4 this way. This time we're approaching a height of -1, so this limit would be equal to -1. If it helps, pretend you're this tiny little ant and this graph is something you're walking on. If you walk from the positive side, when you get really, really close to 4, you're standing right here at a height really close to -1. But if you're walking from the negative side, if you're coming in this direction, then when your x value gets close to 4, you're standing, I don't know, hard to draw these stick figures, somewhere down here, and your height is getting really close to -7. If you can look at this graph and evaluate these different one-sided limits, then you're good. That's the only topic of this video. But you might wonder, what if somebody gave you this graph and just said, what is the limit as x approaches 4, and didn't put this superscript on it? Am I coming from the left? Am I coming from the right? Do I have two different answers? Is my answer the average of these two? What do I do? Well, if you're in the case where the two one-sided limits don't agree, if the limit from the right is different than the limit from the left as we approach 4, then the limit as x approaches 4 of this function does not exist. Which sort of makes sense, right? If I just give you this graph and I say, what height do you get really, really close to when your x value gets really, really close to 4, you'd be like, well, it depends. If I'm the green guy, I'm getting close to -1. If I'm the blue guy, I'm getting close to -7. I get different answers. If there's different answers, we can't evaluate this limit. Contrast that with the case that we saw up here where the person walking from the left gets really, really close to a height of 8, and the person walking from the right gets really, really close to a height of 8 when they approach this x value of 5. Since they're approaching the same height, we know their limit. If the two one-sided limits agree, if the limit as x approaches 5, for example, of some function f of x is the exact same as the limit as x approaches 5 from the negative side of f of x, then the limit as x approaches 5 of this function f of x, the two-sided limit, exists. What's it equal to? It's equal to that same number. If you get the same answer here that you get here, then that answer is the answer here. To see if this all makes sense, here's a little section in green here where I ask you 4 different questions. And if you can answer these 4 different questions, you understand everything that you need to know about limits. The first one is evaluate f of -2. The second one is asking you the limit as x approaches -2 of this function f of x. The third one is asking you to evaluate the one-sided limit, the limit as x approaches -2, from the negative or left side of f of x. And the fourth is asking you to evaluate the one-sided limit, the limit as x approaches -2, but now from the positive side of f of x. And what do I give you for f of x? I give you this graph. Can you figure those 4 things out? First, what is f of -2? F of -2 is just asking you the question, what comes out of this function when you put -2 into it? Here's -2 right here, the x value that kind of all these questions are based upon. And if you look at this graph, because this circle is filled in, it looks like when I put -2 in, +1 comes out. Therefore, f of -2 evaluates to +1. The answer to this first question is just +1. What about this question? The limit as x approaches -2 of f of x. This one's probably the hardest one in here. If somebody asks you this question, really what you have to do is answer these 2 questions right here. Answer this one, answer this one. If you get the same answer for C and D, that's your answer for B. If you get different answers for C and D, then your answer for B is this limit does not exist. So even though I asked them in this order where I ask you for B before C and D, really to answer B, you have to answer C and D. So let's do that. The limit as x approaches -2 from the negative side, from the left of f of x. The way to think about this is you're a little ant, you're walking along this graph, and you're coming in this direction because you start over here on the negative side. You're walking, you're walking, you're walking, you're getting closer and closer to -2. When you're somewhere in here, you're really close to -2. What is your height approaching when you get really close to -2? It's approaching 1. The limit as x approaches -2 from the negative side of this function is just 1. But what if we're coming from the right side? What if instead of imagining you're this person, imagine you're this person. You're walking along the graph and you're getting closer and closer to -2. And when you're standing somewhere over here, you're super close to -2. What is your height getting really, really close to when your x value gets close to -2? Looks like your height is getting really close to 5. So the limit as x approaches -2 from the positive side of this function f of x is the number 5. This answer is 5. And now that we have answers for C and D, we can answer B. Because C and D are not the same number, this does not exist. If these 2 answers had been the same number, then whatever that number is would have been my answer down here. But they're not the same number. 1's not the same as 5. So this limit does not exist. These one-sided limits can be a little bit complicated, but the good news is we're not going to do a whole lot with one-sided limits in our class. You'll see them in this homework assignment, but going forward, we're really going to concern ourselves most with this case, this removable discontinuity case. And in this removable discontinuity case, the limit from the left is the same as the limit from the right, so we can just look at the two-sided limit a little bit more directly. That said, if I didn't at least mention one-sided limits, well, you couldn't do your homework, and you'd be missing kind of a key concept associated with limits, so now at least you've seen it.